Hello students, this is Aishwarya. Welcome to Sankalpa Learning Solutions, and we are starting with the last session of coordination chemistry. Hope all the three sessions were quite crystal clear. Let us see what we are going to study in the last session of coordination chemistry. So let's get started. So here what we are going to talk about is Werner's theory. ಸೊ ಮಾರ್ಕೆಟ್ ಒಳಗಡೆ ಬಹಳಷ್ಟು ಥಿಯರೀಸ್ ಬಂದು ಏನು ಹೇಳಲಿಕ್ಕೆ ಥಿಯರೀಸ್ ಬಂದು ಅಂತ ಅಂದ್ರೆ ಟು ಎಕ್ಸ್ಪ್ಲೇನ್ ದಿಸ್ ಕೋಆರ್ಡಿನೇಷನ್ ಕಂಪೌಂಡ್ಸ್ ದೇರ್ ಆರ್ ಮೆನಿ ಥಿಯರೀಸ್ ಬೀಂಗ್ ಪ್ರಪೋಸ್ ಬೈ ಡಿಫ್ರೆಂಟ್ ಸೈಂಟಿಸ್ಟ್ ಅಥವಾ ಕೆಮಿಸ್ಟ್ ಅಂತ ಅನ್ಬೋದು. ಲೈಕ್ ವಿ ಹ್ಯಾವ್ ವರ್ನರ್ಸ್ ಥಿಯರಿ, ವಿ ಹ್ಯಾವ್ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ, ವಿ ಹ್ಯಾಡ್ ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಥಿಯರಿ, ವಿ ಹ್ಯಾಡ್ ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ ಥಿಯರಿ, ಲಿಗ್ಯಾಂಡ್ ಫೀಲ್ಡ್ ಥಿಯರಿ, ಈವನ್ ವಿ ಹ್ಯಾಡ್ ಎಲೆಕ್ಟ್ರಾನಿಕ್ ಥಿಯರಿ. ಸೋ ಮೆನಿ ಥಿಯರೀಸ್ ಅಲ್ಲ. ಸೊ ಇನ್ ಆರ್ಡರ್ ಟು ಎಕ್ಸ್ಪ್ಲೇನ್, ಬಟ್ ಹಿಯರ್ ನಾವು ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಚಾಪ್ಟರ್ ಅಲ್ಲಿ ಡಿಸ್ಕಸ್ ಮಾಡುವಂತ ಥಿಯರೀಸ್ ಅಪ್ಪ ಅಂತಂದ್ರೆ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಡಿಸ್ಕಸ್ ಓನ್ಲಿ ತ್ರೀ ಥಿಯರೀಸ್. ಒನ್ ಇಸ್ ವರ್ನರ್ಸ್ ಥಿಯರಿ, ದ ಸೆಕೆಂಡ್ ಒನ್ ಇಸ್ molecular valence bond theory, and we are going to talk about the crystal field theory, which we call it as CFT. Okay, so let us try to understand what is this Werner's theory. Fine. So Werner's theory, Alfred Werner, he was a Swiss chemist. He put forward a theory to explain the formation of complex compounds. In fact, ನಾನು ಏನ್ ಹೇಳ್ಬೋದಪ್ಪ ಅಂತಂದ್ರೆ Werner was the first person to formulate these coordination compounds. ಅಂತಂದ್ರೆ what I'm trying to say here is formulate in the form of formula ಕೊಡೋದು ಫಸ್ಟ್ ಟೈಮ್ ಯಾರು ಮಾಡಿದ್ರು ಕೋಆರ್ಡಿನೇಷನ್ ಕಂಪೌಂಡ್ಸ್ ಅಂತ ಅಂದ್ರೆ ಇಟ್ ವಾಸ್ ಬೀಂಗ್ ಗಿವನ್ ಬೈ ವರ್ನರ್. ಸೊ ಹೌ ಡಿಡ್ ವರ್ನರ್ ಮ್ಯಾನೇಜ್ ಟು ಡೂ ಆಲ್ ದೀಸ್ ಥಿಂಗ್ಸ್? ಫಾರ್ಮ್ಯುಲೇಟ್ ಹೇಗ್ ಮಾಡಿದ್ರು? ಸೊ he was even one more thing what I want to say here is he was the first person to speak about something called primary valency and secondary valency. Now you may say, okay, understood, valency ಬಗ್ಗೆ ನಮಗೆ ಗೊತ್ತು, it is the combining capacity of a particular atom ಅಂತ. ಹೌ ಮಚ್ ಇಟ್ ಕಂಬೈನ್ಸ್ ಅಂದ್ರೆ ಎಷ್ಟು ಕಂಬೈನಿಂಗ್ ಕೆಪಾಸಿಟಿ ಇದೆ ಅದನ್ನ ನಾವು ವ್ಯಾಲೆನ್ಸಿಯಲ್ಲಿ ರೂಪಲ್ಲಿ ನಾವು ನೋಡ್ತೀವಿ. ಬಟ್ ವಾಟ್ ಈಸ್ ದಿಸ್ ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿ ಅಂಡ್ ಸೆಕೆಂಡರಿ ವ್ಯಾಲೆನ್ಸಿ? what was Werner trying to tell us through this? So come on, let's see what he wanted to say. So it was the first successful explanation, became famous as coordination theory of complex compounds, which is also known as Werner's theory. So what Werner tried to say through this theory, he gave certain postulates. Werner proposed the coordination theory to explain bonding in the complex molecules. ಹೇಗೆ ಬಾಂಡಿಂಗ್ ಆಗತ್ತೆ ಅದನ್ನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ರು. ಓಕೆ, ಹೌ ಡಿಡ್ ಹಿ ಎಕ್ಸ್ಪ್ಲೇನ್? ಸೊ ಹಿ ಟುಕ್ ಸಮಥಿಂಗ್ ಕಾಲ್ಡ್ ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿ ಮತ್ತು ಸೆಕೆಂಡರಿ ವ್ಯಾಲೆನ್ಸಿ. See, central metal atom or ion in a coordination compound, it exhibits two types of valencies anta andru. One was primary and another one was secondary. So primary valency bandbittu, what is this primary valency? Primary valencies are ionizable and correspond to the number of charges on the complex ion. ಆ ಕಾಂಪ್ಲೆಕ್ಸ್ ಅಯಾನ್ ಮೇಲೆ ಎಷ್ಟು ಚಾರ್ಜ್ ಇದೆ, ದ್ಯಾಟ್ ಈಸ್ ದ ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿ ಅಂತ ಅಂದ್ರು. ಅಂದ್ರೆ ನಾವು ಅದನ್ನ ಆಕ್ಸಿಡೇಷನ್ ಸ್ಟೇಟ್ ಅಂತ ಅನ್ಬಹುದು. ಸೊ ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿ ಅಂತ ಅಂದ್ರೆ, ಸೊ ವೆನ್ ಐ ಸ್ಪೀಕ್ ಅಬೌಟ್ ದ ವರ್ನರ್ಸ್ ಥಿಯರಿ ವೇರ್ ವಿ ಟಾಕ್ ಅಬೌಟ್ ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿ ಅಂಡ್ ದ ಸೆಕೆಂಡರಿ ವ್ಯಾಲೆನ್ಸಿ, ಪ್ರೈಮರಿ ವ್ಯಾಲೆನ್ಸಿಯಲ್ಲಿ ಅವ್ರು ಏನ್ ಹೇಳಿದ್ರು, ಇಟ್ ಈಸ್ ದ ನಾನ್ ಡೈರೆಕ್ಷನಲ್ ವ್ಯಾಲೆನ್ಸಿ. ಅದು ನಾನ್ ಡೈರೆಕ್ಷನಲ್ ವ್ಯಾಲೆನ್ಸಿ. ಅಂಡ್ ಸೊ ಲೆಟ್ ಮಿ ರೈಟ್ ಹಿಯರ್. So there were two things. One was primary valency, which can be abbreviated as PV. Yes. And what is this PV? It is non-directional. It is non-directional. It is non-directional and ionizable anta andru. It is non-directional and ionizable. It is, in fact, it is the positive charge on the metal ion. Yenidu? It is the positive charge. It is the positive charge carried by metal ion, central metal ion, athwa atom anbodu. Okay, this is primary valency. Then what is secondary valency? Secondary valency na heng define madidru? So what do we mean by secondary valency? So secondary valency bandbittu, so secondary valency, it is directional So it is directional. Andre directional antandre ಏನು ಹೇಳಿ ನೋಡೋಣ. See, he was talking about central metal and the ligand. So how many ligand was the one? What is ligand? ನೀವು ಹೇಳಿ ನೋಡೋಣ. Ligand ಅಂತಂದ್ರೆ it is the one which is going to share the electron pair. So donate ಮಾಡುತ್ತೆ ಅದು through its donor atom. So directional, ಯಾವ direction ಅಲ್ಲಿ sharing ಆಗ್ತಾ ಇದೆ? That was being spoken by secondary valency. It is directional and it is non-ionizable. It is non-ionizable secondary valency. Howda? So what it is actually? What is secondary valency? It is equal to the number of ligand atoms. The number of ligand atoms ಅಥವಾ ligand groups ಅನ್ಬೋದು coordinated to the central metal atom. Coordinated to the central metal atom. So can I use the term here coordination number? ಹೌದೇನಲ್ಲ? So that is nothing but coordination number ಅಲ್ಲ? So this is nothing. Secondary valency is nothing but what? Secondary valency is nothing but coordination number. So primary valency ಮತ್ತು secondary valency ನ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿಕ್ಕೆ let us take an example. So I say I have example CO, NH3 6 and Cl3. This particular coordination complex can be written as ions ಅಲ್ಲಿ ಬರಿಬೇಕಂದ್ರೆ ನಾವು ಹೇಗೆ ಬರಿತೀವಿ ಹೇಳಿ? It can be written as CO, NH3 6 plus 3 and 3Cl minus. Correct? So these are the two ions. So this is ionizable primary valency. Howda? Fine. So how much is the primary valency here? The primary valency, how much is the primary valency? It is 3. Primary valency is 3. And how much is the secondary valency? Heli nodana. Secondary valency is 6 because 6 NH3 molecules are coordinated through coordinate bond. They are attached to the central metal atom. So secondary valency is 6. Take another example to make it more clear. So let me say I have CO, again cobalt, NH3 5 Cl. It is NH3 5 Cl, then Cl2. So how does it ionize? Come on, tell me. It ionizes as CO, NH3 5 plus 2 and 2Cl minus ions. Howda? So this is how we write. Now tell me which are the primary valencies. What is the primary valency? Primary valency is, it is 2. And what is the secondary valency? Secondary valency, how many? Okay, I have not written here. So it is Cl also. Howda? Cl is there inside. Howdenilla? So how much is the secondary valency? Come on, tell me. Secondary valency is, it is 6. ಯಾಕೆ ಹೇಳಿ ನೋಡೋಣ? Because 5 NH3 molecules and 1 Cl atom. Yes or no? So secondary valency is 6. So like this you can speak about the primary and the secondary valencies. Take one more example and let me know. It is CO, NH3 4 Cl2, then Cl. Okay, how it ionizes? It ionizes as CO, NH3 4 Cl2 plus and Cl minus. Howda? Is that right? So tell me the primary valency here. What will be the primary valency? Primary valency ಬಂದ್ಬಿಟ್ಟು it will be 1. ಯಾಕಂದ್ರೆ Cl minus 1 ಇದೆ. And secondary valency ಎಷ್ಟು? Secondary valency is nothing but 4 and 6. So here this is the secondary valency. Getting? So primary valency is non-directional. That is nothing but the positive charge carried by the metal ion. Ashte. It is primary valency. So I can say primary valency as ಏನಂತ ಅನ್ಬೋದು? We can say it as oxidation state, oxidation number and oxidation charge ಅಂತ ಅನ್ಬೋದು. So primary valency can be my oxidation number. oxidation number. And now what is secondary valency? Secondary valency is nothing but it is equal to the number of ligands which are attached to the central metal atom, which are coordinated to the central metal atom. Therefore, ligands ಎಷ್ಟಿದಾವೆ ಅಂತ ಹೇಳ್ತೀವಿ ಅಂತಂದ್ರೆ it is nothing but the coordination number. So this is about primary and secondary valency. This was what being spoken for the first time by Werner. So primary valencies are ionizable, they are non-directional and correspond to the number of charges on the complex ion. Number of charges on the complex ion. Primary valencies apply equally well to simple salts also and to complexes and are satisfied by negative ions. They are satisfied by negative ions. Secondary valencies ಬಂದ್ಬಿಟ್ಟು, what are secondary valencies? They correspond to the valencies that the metal atom or ion towards neutral molecules or negative ions. Andre, they are speaking about ligands, correct? Secondary valencies are directional and so a complex has particular shape. Since they are directional, complex will have a particular shape. How the? So the number of arrangements, the number and the arrangement of the ligands, the number and arrangement of the ligands in space determines the stereochemistry of the complex. So here you can see coordination number is nothing but secondary valency, and in this particular example secondary valency is 6 because 6 NH3 molecules are coordinated here. Is that right? So the postulates of Werner's coordination theory were actually based on the experimental evidence. This particular postulates or ಹೇಗೆ ಕೊಟ್ರಪ್ಪ ಅಂತಂದ್ರೆ it was based on certain experiment which was being done by postulate, which was being done by Werner. ಏನಪ್ಪ ಅವರು ಏನಂತ ಇದನ್ನ ಏನಂತ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಿದ್ರು? ಎಕ್ಸ್ಪೆರಿಮೆಂಟಲಿ he spoke about these postulates, whatever we are talking now. ಹೌದಾ? So what he did there, what he actually spoke about was he took certain molecules. ಅವರು ಕೆಲವೊಂದು ಕಂಪೌಂಡ್ಸ್ ತಗೊಂಡ್ರು. ಸೊ ನೇಚರ್ ಆಫ್ ದ ಕಾಂಪ್ಲೆಕ್ಸ್ ಕ್ಯಾನ್ ಬಿ ಅಂಡರ್ಸ್ಟುಡ್. ಅವ್ರು ಏನ್ ಮಾಡಿದ್ರು ಆ ಕಂಪೌಂಡ್ ನ ತಗೊಂಡು, ವಾಟ್ ಕಂಪೌಂಡ್ ಹಿ ಟುಕ್ ಆಲ್ಸೋ ಐ ಟೆಲ್ ಯು. ಹಿ ಟುಕ್ ದ ಕಂಪೌಂಡ್, ಐ ರೈಟ್ ಹಿಯರ್, ಯು ಕ್ಯಾನ್ ಸಿ COCl3 6NH3. He took this compound, then he took COCl3 5NH3, then COCl3 4NH3, COCl3 3NH3. He took these molecules, okay, and he treated these complexes with excess of AgNO3. Pratiyondunu he treated with AgNO3. What is AgNO3? AgNO3 is silver nitrate. AgNO3. Pratiyondu compound he treated it with silver nitrate. Yes, what he found was he got white precipitate in all the cases. When he treated all the compounds with excess of AgNO3, he got white precipitate. Okay, so what he actually got here? He got so I'll write it here, CONH3 6Cl3. This was what he got. Then here CONH3 5Cl, I'm sorry, CONH3 5Cl2. And here he got CONH3 4Cl2Cl, and last CONH3 3Cl3 and no chloride. So you can see here, if I talk about the ions, okay, ions ಬಗ್ಗೆ ಮಾತಾಡಿದ್ರೆ, in the first case, how many ions are there? What are these ions? Chloride ions. So how many? There were 3 chloride ions. ಹೌದಾ? 3 chloride ions. Okay. In the second case, tell me how many are there? There are 2 chloride ions. There are 2 chloride ions. In the third case, there is only 1 chloride ion. ಹೌದಾ? Chloride ion. So this was the experimental observation, and here outside no chloride ion. No chloride ion. So you can see here there are 3 chloride ions, 2. So ionize adaga, so these separate out alla, this becomes plus, this becomes minus, separate agutte. So how many chloride ions? In the first case there were 3. So the nature and bonding between the central metal atom and the ligands in the coordination sphere has been explained, okay, by ವರ್ನರ್ ಏನ್ ಹೇಳಿದ್ರಪ್ಪ ಅಂತಂದ್ರೆ, ವಾಟ್ ಹಿ ಡಿಡ್ ವಾಸ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದಿಸ್, ಹಿ ಮೇಡ್ ದೆಮ್, he found out the conductivity of these solutions, and he found that in the first case the conductivity was maximum. The conductivity was maximum. So ಇಲ್ಲಿ ನಾವು ನೋಡಿದ್ರೆ we'll come to a conclusion. Ions ಹೇಗಿದೆ ಹೇಳ್ರಿ, this is plus and this is minus. So can I write how many ions? The ions are in the form 1:3 electrolytic ratio. ಹೌದಾ? So 1 and these are 3. Here it is 1:2. Here it is 1:1. Yes or no? And here it is only 1. There is no negative ion. How they nila? So the conductivity was found maximum in the first case. In this first case, the conductivity was found maximum. Maximum agittu. Now, when the conductivity will be maximum, come on, tell me. Solutions ಅಲ್ಲಿ conductivity maximum ಇದೆ ಅಂತಂದ್ರೆ ಏನದಕ್ಕೆ ಕಾರಣ? The reason is that ಆ ಪರ್ಟಿಕ್ಯುಲರ್ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಕಂಡಕ್ಟಿವಿಟಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಇದೆ ಅಂತ ಅಂದ್ರೆ ದೇರ್ ಆರ್ ಮೋರ್ ನಂಬರ್ ಆಫ್ ಅಯಾನ್ಸ್ ಅಂತ ಅರ್ಥ. ಹೌದಾ? ಸೊ ಮೋರ್ ನಂಬರ್ ಆಫ್ ಅಯಾನ್ಸ್ ಇದ್ದಾಗ, ಬಿಕಾಸ್ ಅಯಾನ್ಸ್ ಆರ್ ದ ಚಾರ್ಜ್ ಕ್ಯಾರಿಯರ್ಸ್ ಇನ್ ದ ಸೊಲ್ಯೂಷನ್ಸ್. ಎಸ್ ಆರ್ ನೋ? ಸೊ ಅಯಾನ್ಸ್ ಜಾಸ್ತಿ ನಂಬರ್ ಇದ್ದಕ್ಕೆ ಕಂಡಕ್ಟಿವಿಟಿ ಜಾಸ್ತಿ ಆಯ್ತು. ಸೊ ಇನ್ ದ ಫಸ್ಟ್ ಕೇಸ್ ದ ನಂಬರ್ ಆಫ್ ಅಯಾನ್ಸ್ ಆರ್ more. In the second case, the number of ions go on decreasing. Yes, therefore the conductivity also went on decreasing. This was the experiment which was being done by Werner. So this further he explained also the concepts here, what he said. But although Werner's theory was successfully explained the bonding features in coordination compounds, but he had few drawbacks also. Therefore it was not being, though he was the first one to speak about the formulation of the compounds, he was the first one to speak about something called primary valency and secondary valency. Due to certain drawbacks, the theory was not successful enough. So what are the drawbacks? The drawbacks are something like this. It does not explain why only certain elements form coordination compounds. ಯಾಕೆ ಎಲ್ಲ ಎಲಿಮೆಂಟ್ಸ್ ಕೋಆರ್ಡಿನೇಷನ್ ಕಂಪೌಂಡ್ಸ್ ಆಗಲ್ಲ? Why only certain elements are capable of forming a coordination compounds was not explained by Werner's theory ಅಂತ ಅನ್ಬೋದು. It does not explain why the bonds in the coordination compounds have directional properties. ಹೌದು, ಡೈರೆಕ್ಷನಲ್ ಪ್ರಾಪರ್ಟೀಸ್, ಕೋಆರ್ಡಿನೇಟ್ ಬಾಂಡ್ಸ್ ಇದಾವಲ್ಲ, ಡೈರೆಕ್ಷನಲ್ ಪ್ರಾಪರ್ಟೀಸ್ ಇರುತ್ತೆ. ವೈ ಇಟ್ ವಾಸ್ ಹ್ಯಾವಿಂಗ್ ಡೈರೆಕ್ಷನಲ್ ಪ್ರಾಪರ್ಟಿ ವಾಸ್ ನಾಟ್ ಬೀಂಗ್ ಎಕ್ಸ್ಪ್ಲೇನ್. ಇಟ್ ಡಸ್ ನಾಟ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ದ ಕಲರ್ ಅಂಡ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಅಂಡ್ ದಿ ಆಪ್ಟಿಕಲ್ ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ದಿ ಕಾಂಪ್ಲೆಕ್ಸಸ್. ಸಿ ಇಫ್ ಯು ಲುಕ್ ಅಟ್ ದ ಕಾಂಪ್ಲೆಕ್ಸಸ್ ನೆಕ್ಸ್ಟ್ ಥಿಯರೀಸ್ ಅಲ್ಲಿ ಬಂದಾಗ ಯು ವಿಲ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಇಟ್ ಇನ್ ಅ ಬೆಟರ್ ಫಾರ್ಮ್. ದ ಕಲರ್ ಆಫ್ ದ ಕಾಂಪ್ಲೆಕ್ಸಸ್ ಹೇಳ್ಬಹುದು, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಪ್ರಾಪರ್ಟಿ ವೆದರ್ ಇಟ್ ಇಸ್ ಗುಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಕಂಡಕ್ಟ್ ಮಾಡತ್ತಾ ಅಥವಾ ಇಟ್ ಇಸ್ ಲೆಸ್, ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಇಸ್ ಹೈ ಆರ್ ಮ್ಯಾಗ್ನೆಟಿಸಮ್ ಇಸ್ ಲೋ, ಪ್ಯಾರಾಮ್ಯಾಗ್ನೆಟಿಕ್ ಇದೆನಾ ಡಯಾಮ್ಯಾಗ್ನೆಟಿಕ್ ಇದೆನಾ ಅದನ್ನೆಲ್ಲ ಹೇಳ್ಬೋದು ನಾವು. But Werner's theory did not explain that. Even the optical properties of the complexes was not explained by the Werner's theory. So because of these drawbacks, the theory was not successful. So you can see here, this was Werner's modern electronic theory of valence compounds. So you can see how the theory was being explained. So ionization sphere is here. So conducting polymer. So this was how it was being explained. Now applications of Werner's theory to cobalt-3 amines. So this was what I told. So on heating with HCl at 373 Kelvin, cobalt and amines does not evolve NH3. Primary valency of cobalt is 3. You can see here in all the cases, primary valency is 3, secondary valency is 6. All the compounds differ in their reactivity. ಯಾಕೆ ಡಿಫರ್ ಆಗ್ತವೆ ಹೇಳಿ? ಬಿಕಾಸ್ ನಂಬರ್ ಆಫ್ ಅಯಾನ್ಸ್ ಆರ್ ಡಿಫರೆಂಟ್. 1:3, 1:2, 1 ಹೇಳಿದ್ದೆ ಅಲ್ಲ ನಾನು. ಸೊ ಹಿಯರ್ ಇಟ್ ಶುಡ್ ಬಿ 1. ಎಸ್, ನಂಬರ್ ಆಫ್ ವ್ಯಾಲೆನ್ಸೀಸ್ ಏನಾಗುತ್ತೆ? ದೇ ಡಿಫರ್. ಎಸ್, therefore they were differing in the reactivity. So Werner's theory, you can see here the same thing what I spoke about. Yes or no? Werner proposed putting all the molecules and ions within spheres in the brackets, and those free anions that dissociated from the complex ion when dissolved in water outside the bracket. ಇದನ್ನ ಫಸ್ಟ್ ಫಾರ್ಮುಲೇಟ್ ಮಾಡಿದ್ದೆ ವರ್ನರ್ ಅವರು. ಸೊ ಇಲ್ಲಿ ನಾವು ನೋಡ್ಬೋದು. ಸೊ ಅವ್ರು ಏನ್ ಮಾಡಿದ್ರು, ಯಾವುದು ಫ್ರೀ ಇಲ್ಲ, ಯಾವ ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಆಟಮ್ಗೆ ಅಟ್ಯಾಚ್ಡ್ ಇದಾವಲ್ಲ, ಅದು ಹಿ ಪುಟ್ ಇಟ್ ಇನ್ ಟು ದ ಸ್ಕ್ವೇರ್ ಬ್ರಾಕೆಟ್. ಯಾವ ಈಸಿಯಾಗಿ ಅಯೋನೈಸ್ ಆಗ್ತಾವಲ್ಲ, ದೋಸ್ ಹಿ ಪುಟ್ ಇಟ್ ಔಟ್ಸೈಡ್. ಅಂದ್ರೆ ಕಾಂಪ್ಲೆಕ್ಸ್ ಸ್ಪಿಯರ್ ಮತ್ತು ಅಯೋನೈಸೇಷನ್ ಸ್ಪಿಯರ್, ಕೋಆರ್ಡಿನೇಷನ್ ಸ್ಪಿಯರ್ ಮತ್ತು ಅಯೋನೈಸೇಷನ್ ಸ್ಪಿಯರ್ ಆಗಿ ಬರ್ದಿದ್ದು ಫಸ್ಟ್ ಟೈಮ್ ಯಾರಪ್ಪ ಅಂತಂದ್ರೆ ಇಟ್ ಇಸ್ ವರ್ನರ್. ಹೌದಾ? ಸೊ ಯು ಕ್ಯಾನ್ ಸಿ. So this was the experiment which was being done. So COCl3 6NH3, it was orange in color. COCl3 5NH3, purple in color. COCl3 4NH3, green in color. COCl3 3NH3, it was violet in color. So ions per formula unit, you will get 4 ions here, you will get 3, 2 and 2. Okay, it was 4 only. Free Cl minus ions, how many Cl minus ions he was getting? It was none ಬರ್ದಿದೆಯಲ್ಲ, 1:3 ratio, 1:2 ratio, 1:1 ಬರ್ದಿದೆಯಲ್ಲ. So this was these many free ions he was getting. So here if you see modern formulation, he gave the formula like this: COCl36Cl3. Outside, andre this became cation, this became anion. So this is coordination sphere and this is ionization sphere. This was for the first time explained by Werner. Then COCl3 CONH3 5 Cl Cl2. So outside there are two Cl minus ions, and here there is only one Cl minus ion, and here is so cis and trans, you can see. Yes, so this was being done by whom? It was being explained by Werner for the first time. So Adruno with certain drawbacks, the theory was not that successful anta helbodu. Hauda? Fine. So ligands. So we have spoken about the ligands here. Coming to the next one. So all this is being discussed. Bonding in the coordination compounds. ಹೇಗಪ್ಪ ಇದು ಬಾಂಡಿಂಗ್ ಬಗ್ಗೆ ಹೇಗೆ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದು? ಹೌ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದ ಬಾಂಡಿಂಗ್? ಟು ಎಕ್ಸ್ಪ್ಲೇನ್ ದ್ಯಾಟ್ ದೆರ್ ವಾಸ್ ದ ಫಸ್ಟ್ ಒನ್ ವಿಚ್ ವಾಸ್ ಗಿವನ್. ನಾನು ಹೇಳಿದೆ ಬಹಳಷ್ಟು ಥಿಯರೀಸ್ ಬಂದು ಮಾರ್ಕೆಟಲ್ಲಿ ಅಂತ, ಬಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಡಿಸ್ಕಸ್ ಓನ್ಲಿ ಫ್ಯೂ. ಒಂದೇದು ಬಂದ್ಬಿಟ್ಟು valence bond theory, then VBT, crystal field theory, CFT, ligand field theory, LFT, molecular orbital theory, MOT. ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ಮತ್ತು ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ ಥಿಯರಿ ಸರ್ಟನ್ ಇನಾರ್ಗ್ಯಾನಿಕ್ ಕಾಂಪೌಂಡ್ಸ್ ಅಲ್ಲಿ ನಾವು ಆಲ್ರೆಡಿ ನೋಡಿದೀವಿ. ಅಂಡ್ ದೇರ್ ಆರ್ ಸಿಮಿಲಾರಿಟೀಸ್ ಆಲ್ಸೋ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ ಹಿಯರ್. ಎಸ್, ಸೊ ವಾಟ್ ಈಸ್ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ? Linus Pauling in the year 1931 spoke about valence bond theory of 1931. The valence bond theory satisfactorily explains the structure and magnetic properties of large number of coordination compounds. See, ಯಾವುದು ಡ್ರಾಬ್ಯಾಕ್ ಆಗಿತ್ತು ವರ್ನರ್ಸ್ ಥಿಯರಿಯಲ್ಲಿ, ದಟ್ ವಾಸ್ ಬೀಯಿಂಗ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಬೈ ಒನ್ ಆಫ್ ದ ಡ್ರಾಬ್ಯಾಕ್ ವಾಸ್ ಬೀಯಿಂಗ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಬೈ ವ್ಯಾಲೆನ್ಸ್ ಬಾಂಡ್ ಥಿಯರಿ. ವಾಟ್ ವಾಸ್ ದ ಡ್ರಾಬ್ಯಾಕ್? ಸ್ಟ್ರಕ್ಚರ್ ಮತ್ತು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಪ್ರಾಪರ್ಟೀಸ್ ಹೇಳಲಿಕ್ಕೆ ಆಗಲಿಲ್ಲ, ಹೌದಾ? ಸೊ ದ್ಯಾಟ್ ವಾಸ್ ಬೀಯಿಂಗ್ ಕ್ಲಿಯರ್ಲಿ ಎಕ್ಸ್ಪ್ಲೇನ್. Now what the suitable number of atomic orbitals of the central metal atom? ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಆಟಮ್ ಅಲ್ಲಿ SPDF ಬಗ್ಗೆ ನಮಗೆ ಗೊತ್ತು. ಸೊ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಆಟಮ್ ಅಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ suitable number of atomic orbitals, they will hybridize to provide empty hybrid orbitals. ಅವು ತಂತಾನೆ ಹೈಬ್ರಿಡೈಸ್ ಆಗ್ತವೆ. ಹೈಬ್ರಿಡೈಸೇಷನ್ ಬಗ್ಗೆ ನೀವು ಕಲ್ತಿದ್ದೀರಿ PU1 ಕ್ಲಾಸಸ್, ಅದರ ಬಗ್ಗೆ ನಾನು ಹೇಳೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ. ಸೊ they will hybridize to give you hybrid orbitals, ಅಂದ್ರೆ new orbitals with equivalent energies. ಸ್ವಲ್ಪ ಡಿಫರೆನ್ಸ್ ಇನ್ ಎನರ್ಜೀಸ್ ಇರೋಂಥ ವೇಕಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಅವೆಲ್ಲ ಇಂಟರ್ಮಿಕ್ಸಿಂಗ್ ಆಗಿ ದೇ ವಿಲ್ ಫಾರ್ಮ್ ದ ನ್ಯೂ ಸೆಟ್ ಆಫ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಂಡ್ ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಂಡ್ ದ ಫೆನಾಮಿನನ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಹೈಬ್ರಿಡೈಸೇಷನ್. ಹೌದಾ? ಸೊ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್ ಫಾರ್ಮ್ ಆದಾಗ ಎಫ್ ಸೀನ್ ಒಂದು ಎಸ್ ಆಮೇಲೆ ಒಂದು ಪಿ ಆರ್ಬಿಟಲ್ ಹೈಬ್ರಿಡೈಸ್ ಆಯ್ತಂದ್ರೆ ಇಟ್ ಫಾರ್ಮ್ಸ್ SP ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್, 2 ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್. ಎಷ್ಟು ವೇಕಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಹೈಬ್ರಿಡೈಸ್ ಇಂಟರ್ಮಿಕ್ಸ್ ಆಗ್ತಿದಾವಲ್ಲ ಅಷ್ಟೇ ನಮಗೆ hybrid orbitals form ಆಗಿರುತ್ತೆ. For example, 1 s orbital, 1 p orbital. So how many? There are 2 orbitals involved and that will intermix to give me 2 new hybrid orbitals and those will be called sp hybrid orbitals. 1s, 2p. So there are 3. Therefore, they will intermix and they will give me 3 new set of orbitals which are called sp2 hybrid orbitals. 1s and 3p, sp3 hybrid orbitals, I'll get 4. Yes, then 1d, 1s and 3p, dsp2, dsp3. ಹೀಗೆ ನಮಗೆ ವೇರಿಯಸ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ ಸಿಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಹಿಯರ್ ವಾಟ್ ದೇ ಆರ್ ಟ್ರೈಂಗ್ ಟು ಸೇ, ದ ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಆಟಮ್ ಆರ್ ಅಯಾನ್ ಹ್ಯಾಸ್ ರಿಕ್ವೈರ್ಡ್ ನಂಬರ್ ಆಫ್ ವೇಕಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಫಾರ್ ಅಕೊಮಡೇಟಿಂಗ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಡೊನೇಟೆಡ್ ಬೈ ಹೂಮ್? ಡೊನೇಟೆಡ್ ಬೈ ದಿ ಲಿಗ್ಯಾಂಡ್ಸ್. ಹೌದಾ? ಸೊ ಆ ಲಿಗ್ಯಾಂಡ್ಸ್ ಹಾಕೊಳ್ಳಿಕ್ಕೆ ಒಂದು ಜಾಗ ಬೇಕಲ್ವಾ? ಸಮನ್ ಇಸ್ ಗಿವಿಂಗ್ ಯು ಸಮಥಿಂಗ್ ಅಂದ್ರೆ ಅದನ್ನ ಇಡಕ್ಕೆ ನಿಮ್ಮ ಹತ್ರ ಒಂದು ಸ್ಪೇಸ್ ಬೇಕು. ಸೊ ದಟ್ ಈಸ್ ಅದು ಯಾರ ಹತ್ರ ಇರಬೇಕು? ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಅಯಾನ್ ಹತ್ರ. ಸೊ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್ ಹಿಯರ್ ಇಸ್ ದ ನಂಬರ್ ಆಫ್ ವೇಕಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಕೋಆರ್ಡಿನೇಷನ್ ನಂಬರ್ ಆಫ್ ದ ಮೆಟಲ್ ಅಯಾನ್. ಎಷ್ಟು ಲಿಗ್ಯಾಂಡ್ಸ್ ಬಂದ್ಬಿಟ್ಟು ದೇ ಆರ್ ಡೊನೇಟಿಂಗ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ ಪೇರ್ಸ್, ದಟ್ ಈಸ್ ದ ನಥಿಂಗ್ ಬಟ್ ನಂಬರ್ ಆಫ್ ವೇಕೆಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಷ್ಟೇ ತಗೊಳ್ಬೋದಲ್ಲ. ಫೈನ್. ಸೊ ವೇಕೆಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಅಂದ ತಕ್ಷಣ ವಾಟ್ ಆರ್ ದೋಸ್, ಎಸ್ ಪಿ ಡಿ ಎಫ್ ಅಂತ ಅಂತೀವಿ. ಸೊ ಹಿಯರ್ ವಾಟ್ ಆಕ್ಚುಲಿ ಇಸ್ ಹ್ಯಾಪನಿಂಗ್, ಸೊ ದೀಸ್ ಹೈಬ್ರಿಡ್ ಆರ್ಬಿಟಲ್ಸ್ ಏನ್ ಮಾಡ್ತಾವಪ್ಪ, ದೇ ವಿಲ್ accept the lone pair of electrons from the ligands and they are directed towards ligand positions. So they will accept. ಯಾಕೆ ಡೈರೆಕ್ಟ್ ಆಗ್ತಾವೆ, ಬಿಕಾಸ್ ಟು ಗಿವ್ ದ ಜಾಮೆಟ್ರಿ, ಟು ಗಿವ್ ದ ಶೇಪ್ ಫಾರ್ ದಟ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್, ಟು ಗಿವ್ ದ ಶೇಪ್ ಫಾರ್ ದಟ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್. ಹೌದಾ? ಸೊ ವಾಟ್ ಆಕ್ಚುಲಿ ಹ್ಯಾಪನ್ಸ್ ಹಿಯರ್ ಇಸ್ vacant orbitals, they go into hybridization to form same number of hybrid orbitals, to form same number of hybrid orbitals. Howda? Fine. Then each ligand has at least one orbital containing lone pair of electrons. Vacant hybrid orbitals filled with ligands to form coordination bond. And this coordination bond is stronger if the overlapping between the orbitals is greater. It is known to us. Overlapping ಜಾಸ್ತಿ ಆಯ್ತಪ್ಪ ಅಂತಂದ್ರೆ the bond becomes stronger. If overlapping is less, the bond becomes weaker. So these hybrid orbitals ಏನದಾವಲ್ಲ, the new set of hybrid orbitals, ಎಷ್ಟು overlap vacant orbitals overlap ಆಗಿದಾವ ಅಷ್ಟೇ hybrid orbitals form ಆಗಿರುತ್ತೆ. Those hybrid orbitals ಏನು speciality, they will have equivalent energies. The hybrid orbitals will have equivalent energies. They will accept the lone pairs donated by the ligands. When inner d orbitals, let me speak about that also. ಯಾವಾಗ ಇನ್ನರ್ ಡಿ ಆರ್ಬಿಟಲ್ಸ್, ಇದು ದಿಸ್ ಆಲ್ಸೋ ಶುಡ್ ಬಿ ನೋನ್ ಟು ಯು ಆಲ್. ಇನ್ನರ್ ಡಿ ಆರ್ಬಿಟಲ್ಸ್ ಯೂಸ್ ಆದಾಗ ಯಾವ ತರದ್ದು ಹೈಬ್ರಿಡೈಸೇಷನ್ ಆಗುತ್ತೆ ಅಂಡ್ ಔಟರ್ ಡಿ ಆರ್ಬಿಟಲ್ಸ್. ಸೊ ಐಲ್ ರೈಟ್ ಹಿಯರ್, ವೆನ್ ಇನ್ನರ್ ಡಿ ಆರ್ಬಿಟಲ್ಸ್, when inner d orbitals andre, that is n minus 1d orbitals are used in hybridization, are used in hybridization, the complex is called, the complex is called inner orbital complex, inner orbital complex, or it is also called as spin or hyperligated complex. Hyperligated complex. And when outer d orbitals are involved, outer d orbitals and the n d orbitals are involved, it is called outer d orbitals involved idaga, it is called outer orbital complex or outer orbital complex. Now in this case, one more thing what we need to understand here is, if a substance do not contain any unpaired electrons, if that particular compound has no unpaired electrons, no unpaired electrons, no unpaired electrons, then it is not attracted by the magnetic field and it is said to be diamagnetic. It is said to be diamagnetic. Yes, and if it is having the unpaired electrons, if it contains one or more unpaired electrons, if the substance has one or more unpaired electrons, then it is said to be paramagnetic. It is said to be paramagnetic. So unpaired electrons ittappa antandre it is paramagnetic, unpaired electrons irlillappa antandre diamagnetic. And this paramagnetism ಎಷ್ಟು magnetic field ಗೆ attract ಆಗುತ್ತೆ can be measured by certain expression which is called spin magnetic moment. Mu stands for magnetic moment, is equal to root of n into n plus 2 Bm. Bm stands for Bohr magneton. S is spin only value, mu is magnetic moment, and n is number of unpaired electrons. Number of unpaired electrons. So you can measure the magnetic moment using this expression. So if I can say, if n is equal to 1, n 1 itappa antandre, what will be mu s? Mu s is equal to root of 1 into 1 plus 2. 1 plus 2 is 3. So this is root 3, which is nothing but 1.73 Bohr magneton. So this is how you can measure the magnetic moment of the paramagnetic substances. So on the basis of the value of this magnetic moment, we can predict the number of unpaired electrons present also. If we know the number of unpaired electrons in the complex, then it is possible to predict the geometry of the compound. So valence bond theory idanne ಹೇಳಿತು. It was able to explain the magnetic properties of the compound, and it was also able to explain the structure of the compounds. Howda? So next what it says is there are two types of ligands anta ಹೇಳುತ್ತೆ. There are two types of ligands. There are two types of ligands. This theory says that two types of ligands. This is very important part you need to understand. So which are those two types? One is strong field ligands. Strong field ligands. And the another one is weak field ligands. Weak field ligands. So strong field ligands anta andre ಏನು? Strong field ligands is capable of forcing the electrons of the metal atom to pair up. Suppose central metal atom ಅಲ್ಲಿ suppose d orbital ಅನ್ಕೊಳ್ಳೋಣ. So d orbital ಅಂದ್ರೆ 5 subshells we have. Suppose here the electrons are something like this. So ಹೀಗಿದೆ ಅನ್ಕೊಳ್ಳೋಣ. Okay. So strong field ligand ಇತ್ತಪ್ಪ ಅಂತಂದ್ರೆ strong field ligand is approaching hybridization time li ಏನ್ ಮಾಡತ್ತೆ ಅಂದ್ರೆ it will force these unpaired electrons to pair up and this will become like this. So you can see here. So idu higide. So this will make it to pair up and these will be vacant. Understanding? So this is the work of strong field ligands. So it will pairing is done only to the extent which is required to cause hybridization. ಇದನ್ನು ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. ಎಲ್ಲಾನು ಪೇರ್ ಆಗತ್ತೆ ಅಂತ ಹೇಳಕ್ ಬರಲ್ಲ. ಎಷ್ಟು ಹೈಬ್ರಿಡೈಸೇಷನ್ ಅವಶ್ಯಕತೆ ಇದೆ ಅಷ್ಟು ಪೇರಿಂಗ್ ಆಗತ್ತೆ. ಪಾಸಿಬಲ್ ಫಾರ್ ದಟ್ ಕೋಆರ್ಡಿನೇಷನ್ ನಂಬರ್ ಅಂತ ಅನ್ಬೋದು. Weak field ligands anta andre ಏನು? Weak field ligands will not allow the metal atom to pair up. It will not force the metal atom to pair up. So if it is something like this 1 2 3 4 5 and it is something like this ಅನ್ಕೊಳ್ಳೋಣ. So it will not force these if it is a weak field ligand approaching, it will not force the unpaired electrons. Metal atom na force ಮಾಡಲ್ಲ pair up ಆಗ್ಲಿಕ್ಕೆ. This will remain as it is. It will remain as it is. So these are the two types of strong field and weak field ligands. So if I say what are the examples for strong field ligands? Strong field ligands ಬಂದ್ಬಿಟ್ಟು you can have a note. It is Cn minus, then CO, then En, NH3, then you have H2O, then you have NO plus, and then you have Py. These are the examples for strong field ligands. Weak field ligands ಗೆ examples ಬೇಕಂದ್ರೆ all your halos. I minus, Br minus, Cl minus, F minus, NO3 minus, then OH minus, then you have C2O4 minus 2, then you have NH3 also as a, then you have H2O in certain cases. Okay, so these are the strong field ligands ಮತ್ತು weak field ligands ಅಂತ ಹೇಳ್ಬೋದು. Okay, so this is very important to understand valence bond theory. So the vacant d orbitals of the metal atom or ion undergo suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. So you can see here orbitals of CO plus 3 ion. So this is CO plus 3 ion. So here we have vacant 4s and 4p. So 1 4s and 3 4p orbitals. So they will hybridize. Yes. So based on that, we have different geometrical shapes based on the hybridizations. And you can see here, if it is sp hybridization, coordination number ಬಂದ್ಬಿಟ್ಟು ಎಷ್ಟಾಗಿರುತ್ತೆ ಹೇಳಿ 2. Okay, the geometry is linear and here you have the examples. If it is sp2 hybridization, yavaga possible? Coordination number 3 iddaga. So sp2 trigonal planar. 4 coordination number iddaga it is sp3, it can be dsp2 also. Yes, so geometries, if it is sp3 tetrahedral geometry with 4 examples, and if it is dsp2 it is square planar with the examples. 5 coordination number iddaga dsp3. Yes, trigonal bipyramidal with the examples. If n minus 1d orbitals are used for hybridization, the complexes are called inner orbital complexes. Just now I have told n minus 1d use aitandre inner. You can see here inner illi 3 n minus 1d. So here you can see. So ಇಲ್ಲಿ inner d orbitals ಇದೆ. This is outer d orbitals. So this is n minus 1 d orbitals and this is n d orbitals. If n minus 1 d are used in hybridization, it is called inner orbital complex ಅಥವಾ low spin complex ಅಥವಾ spin paired complex ಅಂತ ಅನ್ಬಹುದು. If outer orbitals are d orbitals are used, that is nd orbitals use ಆಯ್ತಪ್ಪ ಅಂತಂದ್ರೆ, it is called outer orbital complex, high spin complex or spin free complex ಅಂತಾನು ಅನ್ಬಹುದು. Yes, this should be known to you all. ಯಾವಾಗ inner d orbitals use ಆಗತ್ತೆ, ಯಾವಾಗ this will be possible when you have strong field ligands ಅಥವಾ weak field ligands ಇದ್ದಾಗ. Okay. So here we have, when strong field ligands like NH3Cn minus are involved in formation of the complexes, they cause pairing. They force the central metal atom to pair up. They force the central metal atom to pair up. So pairing agate. So pairing adaga, yavaga pairing agate when there is strong field ligand. And I gave you the examples of strong field ligands also. They cause pairing of the electrons present in the metal ions. This process is called spin pairing. So structure of the complex is based on VBT. So structures, you can write structure for nickel tetracarbonyl, formation of NiCl4 minus 2 ions. This you have you have done the structures also. So structure of NiCN4 minus 2, we can write the structures for all the compounds. So here is an example, NiCl4 minus 2. So oxidation state of Ni will be plus 2. Each chlorine ion donates how many? 2 electrons, that is 1 pair. So Ni idu configuration ಬಂದ್ಬಿಟ್ಟು 3d8 4s2. So here I'll write 3d8 4s2. 1 2 3 4 5 6 7 8. ಈಗ 4s2 ಇಲ್ಲೇನು 2 electrons ಇದ್ವಪ್ಪ. But Ni it is in which oxidation is it? Plus 2. ಅಂದ್ರೆ 2 electrons from 4s are lost. ಹೌದಾ? So here you can see these are the electrons. Now 4s orbital is vacant, 4p orbitals is vacant. So what hybridization? 1 4s and 3 4p orbitals will involve in hybridization and they will form. Since Cl is there, please note a point, Cl irodrinda, Cl ideyala. So what is my Cl? Cl is my weak field ligand. So this Cl will not force the electrons to pair up, force ಮಾಡಲ್ಲ. Therefore, ಅಕಸ್ಮಾತ್ ಇಲ್ಲಿ ಏನಾದರೂ ಸ್ಟ್ರಾಂಗ್ ಫೀಲ್ಡ್ ಲಿಗ್ಯಾಂಡ್ ಇದ್ದಿದ್ರೆ ಇಟ್ ವುಡ್ ಹ್ಯಾವ್ ಕಾಸ್ಡ್ ಪೇರಿಂಗ್. ಇಲ್ಲಿ ನಮಗೆ ಒಂದು ವೇಕೆಂಟ್ ಡಿ ಆರ್ಬಿಟಲ್ ಸಿಕ್ಕಿರೋದು. ಸೊ ದ ಕಾನ್ಫಿಗರೇಷನ್ ವುಡ್ ಹ್ಯಾವ್ ಬಿನ್ DsP2 ಆಗಿರಬಹುದಿತ್ತು if there was a strong field ligand. But Cl being a weak field ligand will not allow it to pair up. So pair up ಆಗ್ತಿಲ್ಲ. ಸೊ pair up ಆಗ್ತಿಲ್ಲ ಅಂದಮೇಲೆ ಅದು ವೇಕೆಂಟ್ ಇಲ್ಲ. So it is not vacant there. ಹೌದಾ? So vacant ಇದ್ದಿದ್ದ orbitals ಯಾವ್ಯಾವಪ್ಪ? It is 4s and 3 4p. So totally ಎಷ್ಟಾಯ್ತು? 4. So here you have 1 2 3 4. So 4 sp3 dsp3 hybrid orbitals you have got. You have got 4 sp3 hybrid orbitals. And these 4 sp3 hybrid orbitals, so they will accept the pairs of electrons from whom? From 4 Cl minus ions. So they will take pair of electrons from 4 Cl minus ions and they will form the complex. They will form the complex. Howda? So here NiCN4 minus 2 and NiCl4. ಎರಡು ಎಕ್ಸಾಂಪಲ್ಸ್ ಬೇರೆ ಬಾಜು ಬಾಜು ಇದೆ ನೋಡ್ಕೊಂಡ್ಬಿಡಿ. ಸೊ ವಾಟ್ ಈಸ್ ಹ್ಯಾಪನಿಂಗ್ ಹಿಯರ್? ವೆರಿ ಗುಡ್ ಎಕ್ಸಾಂಪಲ್ ವಿ ಕ್ಯಾನ್ ಸಿ. ಸೊ ಯು ಕ್ಯಾನ್ ಸಿ ಹಿಯರ್ NiCN4 ಇದ್ದಾಗ Ni is in plus 2 state. ಹೌದಾ? ಸೊ 2 electrons are lost from 4s. 2 electrons are lost ಅನ್ಕೊಳ್ಳೋಣ. In case of Cn being a strong field ligand, what it has done? It has forced, ಇದು ಹೋಯ್ತಪ್ಪ, ಇದು ಹೋಯ್ತು in Ni plus 2. So it has forced this to pair up. So pair up ಆಗಿದೆ ಇಲ್ಲಿ. Can you see pair up is done? So ಒಂದು D, ಒಂದು S, ಆಮೇಲೆ 2p, 3p ಇದ್ರೂ 3 ಯೂಸ್ ಆಗಲ್ಲ ಡಿಪೆಂಡಿಂಗ್ ಅಪಾನ್ ದ ರಿಕ್ವೈರ್ಮೆಂಟ್ ಅಂತ ಹೇಳಿದ್ದೆ. ಸೊ 2p. ಸೊ ಹೈಬ್ರಿಡೈಸ್ ಆಯಿತು. ಸೊ ಆ್ಯಂಡ್ ಗೇವ್ ಮಿ 1 2 3 4 4 dsp2 hybridization ಆಗತ್ತೆ. 4 pairs of electrons from whom? From Cn minus will come and occupy that place. Correct? So if you look at the geometry of NiCN4 minus 2, it is square planar geometry. It is square planar geometry because hybridization is dsp2. And tell me, are there any unpaired electrons? Look at the structure and tell me, are there any unpaired electrons? No, there are no unpaired electrons. Therefore it is diamagnetic because there are no unpaired electrons. On the other hand, look at NiCl4 minus 2. Cl being the weak field ligand, it cannot force to pair up. So pairing agila. ಪೇರಿಂಗ್ ಆಗಿಲ್ಲ ಅಂದಮೇಲೆ ವೇಕೆಂಟ್ ಆರ್ಬಿಟಲ್ಸ್ ಇಲ್ಲ. ಸೊ ಒಂದು ಎಸ್ ಮತ್ತು 3p ತಗೊಂಡ್ಬಿಟ್ಟು ಇಟ್ ಹ್ಯಾಸ್ ಬಿಕಮ್ sp3 ಹೈಬ್ರಿಡೈಸೇಷನ್. sp3 ಹೈಬ್ರಿಡೈಸೇಷನ್ ಅಂದ ತಕ್ಷಣ ವಾಟ್ ಬಿಕಮ್ಸ್ ದ ಜಾಮೆಟ್ರಿ? 4 Cl ಮೈನಸ್ ಅಯಾನ್ಸ್ ಲಿಂದ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಬಂದ್ಬಿಟ್ಟು ಆಕ್ಯುಪೈ ಆಗಿದೆ ಇಲ್ಲಿ, ಹೌದಾ? ಸೊ ವಾಟ್ ಇಸ್ ದ ಜಾಮೆಟ್ರಿ ಹಿಯರ್? Here the geometry is tetrahedral geometry. It is tetrahedral geometry. So tetrahedral geometry, and you can see there are two unpaired electrons. There are two unpaired electrons. Therefore, this is paramagnetic in nature, and you can calculate mu also. So root of 2 into 2 plus 2. 2 plus 2 is 4. 4 2 is 8. Root of 8 ಎಷ್ಟು ಬರುತ್ತೆ ನೋಡಿ? That will be equal to Bohr magneton. Yes, you can calculate the magnetic moment also. So strong field ligand causes pairing. Weak field ligand does not cause pairing. Adar mele hybridization change agatte. Hybridization also changes. Yes, I hope this point is clear. Then, what were the drawbacks of valence bond theory? See, valence bond theory, it could not explain the color of the complexes. See, valence bond theory failed successfully to explain the qualitatively the geometry and magnetic behavior. It was successful in explaining the qualitatively the magnetic behavior ಮತ್ತು structure, but certain things it could not. ಏನಪ್ಪ ಅದು certain things ಅಂದಾಗ, the origin of their absorption spectra could not be explained. Spectra ಹೇಗ್ ಬಂತು was not being explained. Then why do different complexes of same metal show different colors? Same metal complexes ಇದೆ, but ಬೇರೆ ಬೇರೆ colors ಇದೆ. What was the reason? Relative stabilities of the complexes was not being explained. And then why should certain ligands form high spin while others form low spin? That was also not explained. Very high ligands, low ligands anta ಹೇಳಿತಷ್ಟೇ. But why it was forming high spin and low spin complexes was not being explained by valence bond theory again. So here this was again a failure anta ಅನ್ಬೋದು. So first point, does not explain the color of the coordination compounds, cannot explain magnetic behavior based on the geometry. Okay. Then did not explain why some were called inner complexes and some called outer complexes. Same oxidation state alli iddaga. Fails to predict exact geometries with the help of coordination number 4. Yes, these were the drawbacks of valence bond theory. Then to explain the stability of the complexes, there were different again. So thermodynamics came into context. Stabilities depend upon interactions between metals and the ligands. If interaction, strong thermodynamic stability, the strong depends. Okay, how it was? Reaction between a metal ion and ligand is based on Lewis acid. Lewis acid ಮತ್ತು Lewis base ನಾವು ನೋಡಿದೀವಿ. The one which accepts the electrons is Lewis acid. So central metal atom is Lewis acid, and the one which is donating the ligand is Lewis base. Donating the electron is Lewis base. So ligand is the Lewis base. Greater the value of stability constant, more is the complex. So that stability was being explained through this M plus NL equilibrium. At equilibrium, it become MLN. So here, what was this all about? Charges are being omitted. You apply law of mass action here. You get K is equal to concentration of MLN, number of ligands, divided by polar concentrations of M and L, where K is formation equilibrium constant and K is directly proportional to the stability of the complexes. ಇದನ್ನ ಎಕ್ಸಾಂಪಲ್ ರೂಪಲ್ಲಿ ತಗೊಳ್ಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ I'll just tell you. CuNH3 4 plus 2 ಇದೆ. So equilibrium attained. So I'll write it as I'm sorry. So here I can write it as Cu plus 2 plus 4 NH3 anta baribahudu. So this is given by the expression K is equal to Cu plus 2 NH3 4 by Cu NH3 4 plus 2. Yes. So stability constant for above complex, that is for this complex Cu plus 2 plus 4 NH3 ಇದರದು ಉಲ್ಟಾ ಬರ್ದಾಗ, yes, opposite ಆಗಿ ಬರ್ದಾಗ CuNH3 4 plus 2. This can be given by K is equal to CuNH3 4 plus 2 divided by Cu plus 2 NH3 4. ಹೌದಾ? So I can write it as 1 by K. ಅಥವಾ KI ಅಂತ ಡಿನೋಟ್ ಮಾಡೋಣ. This is stability complex for the first expression. KI ಅಂತ ಡಿನೋಟ್ ಮಾಡೋಣ. So this I can write as, so greater the stability constant, stronger is the metal ligand bond. So what are the factors which affect this stability constant? You can write it like this. So factors ಏನಪ್ಪ stability constant to K dash is the instability constant ಅಥವಾ dissociation constant ಅಂತ ಅನ್ಬೋದು. ಹೆಂಗ್ ಡಿಸೋಸಿಯೇಟ್ ಆಗತ್ತೆ. And what is K is the stability complex. So nature of the central metal atom, factors which affect the stability of the complexes is nature of the central metal ion. So central metal ion ಹೇಗಿರ್ಬೇಕು? Higher the charge density on the central metal ion, greater is the stability ಅಂತ ಅನ್ಬೋದು. Higher the charge, greater the stability. So higher the charge of the central metal atom, greater is the stability. For example, stability constants if you take for FeCN6Li, you can see examples are being shown. ಎಷ್ಟು ಚಾರ್ಜ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ ಸೆಂಟ್ರಲ್ ಮೆಟಲ್ ಆಟಮ್ ಮೇಲೆ ಅಷ್ಟು ಸ್ಟೆಬಿಲಿಟಿ ಜಾಸ್ತಿ ಇದೆ. Then second case, nature of the ligand is also important. Greater the basic strength of the ligand, more will be the ease with which it can donate. ಲಿವೆಸ್ ಬೇಸ್ ಅಲ್ಲ, ಲಿಗ್ಯಾಂಡ್ ಇಸ್ ಅ ಲಿವೆಸ್ ಬೇಸ್. ಸೊ ಅದ್ರ ಬೇಸಿಕ್ ಸ್ಟ್ರೆಂತ್ ಎಷ್ಟು ಜಾಸ್ತಿ ಇರುತ್ತೆ ಅಷ್ಟು ಈಸಿಲಿ ತನ್ನ ಎಲೆಕ್ಟ್ರಾನ್ ಪೇರ್ನ ಇಟ್ ಕ್ಯಾನ್ ಡೊನೇಟ್ ಅಂಡ್ ದೇರ್ ಫಾರ್ ಗ್ರೇಟರ್ ಇಸ್ ದ ಸ್ಟೆಬಿಲಿಟಿ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಇಫ್ ಯು ಟೇಕ್ CuNH3 4+2 ಆರ್ CuCN4+2, ಅವೆರಡದ್ರಲ್ಲಿ ನೋಡಿದಾಗ CuNH3+4 ಇಸ್ ಮೋರ್ ಸ್ಟೇಬಲ್. ಯಾಕೆ ಹೇಳಿ? ಬಿಕಾಸ್ NH3 ಇಸ್ ಮೋರ್ ಈಸಿಲಿ ಡೊನೇಟ್ಸ್ ಇಟ್ಸ್ ಎಲೆಕ್ಟ್ರಾನ್ ಪೇರ್ ಅಂತ ಅನ್ಬೋದು. Then presence of the chelating ring also comes into context. Chelating links form more stable complexes as compared to monodentate ligands. More stable complexes ಆಗತ್ತೆ chelating links ಇದ್ದಾಗ. So this is about ligand field theory. Crystal field theory, what it tells us. The crystal field theory was proposed by Hans Bethe and Van Hag. Crystal field theory assumes that interaction between the metal ion and the ligand is purely electrostatic. So crystal field theory ಏನು ಹೇಳುತ್ತೆ ಅಪ್ಪ ಅಂತಂದ್ರೆ, crystal field theory it was being proposed by Bethe and Leck and was originally applied to ionic crystals to explain their optical properties. Other the optical properties ಹೇಳಲಿಕ್ಕೆ this theory was put forward. Therefore it was called as crystal field theory. So it is based on the assumption that metal ion and the ligands act as point charges. Metal ions ಮತ್ತು ligands, they act as point charges. Interaction between them is purely electrostatic. ಅಂದ್ರೆ ಏನು? Metal ligand bonds are 100% ionic ಅಂತ ಅರ್ಥ. Understanding? So metal ion bonds are 100% ionic. The 5d orbitals is in an isolated gaseous metal, they are degenerate. D orbitals ಅಂದಾಗ ಎಷ್ಟು d orbitals ಇದಾವೆ ಹೇಳಿ? S ಗೆ there is only 1, P is having 3, D is having 5 and F is having 7. So 5d orbitals ಏನಿದಾವಲ್ಲ at the ground state, they are degenerate ಅಂತ ಹೇಳ್ತೀವಿ. Degenerate ಅಂತ ಅಂದ್ರೆ ಏನು? They all have same energy. They all have same energy. Same energy ಇರೋ orbitals ಗೆ ನಾವು degenerate orbitals ಅಂತ ಅಂತೀವಿ. This degeneracy, it is maintained in spherically symmetrical field of negative charges. Negative charges is field and it is maintained. However, when this negative charge of the orbitals, negative charge is due to what? It is due to ligands in charge ಇದೆಯಲ್ಲ, the degeneracy of the d orbitals, it is lifted due to symmetrical field. This results in splitting of the d orbitals. ಏನಾಗತ್ತೆ ಅವಾಗ? degenerate d orbitals with same energy ಇದೆಯಲ್ಲ, they will split because of the ligands negative charge ಇದೆ. Okay, negative charge ಇಂದ. ಸೊ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಆಫ್ ದ ಡಿ ಆರ್ಬಿಟಲ್ಸ್ ಏನಾಗತ್ತಲ್ಲ, ಅದಕ್ಕೆ ನಾವು ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಅಂತ ಅಂತೀವಿ. ಅಂಡ್ ದ ಎನರ್ಜಿ ಪೊಸೆಸ್ಡ್ ಬೈ ದಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಎನರ್ಜಿ, CFSE ಅಂತ ಹೇಳ್ತೀವಿ. ಓಕೆ, ಸೊ ದ ಪ್ಯಾಟರ್ನ್ ಆಫ್ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಡಿಪೆಂಡ್ಸ್ ಅಪಾನ್ ನೇಚರ್ ಆಫ್ ದ ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್. Such as you have octahedral splitting or you have tetrahedral splitting. Early differ agate. See, d orbitals andaga you have dx, dy, dxy, dyz, dzx, dx square, y square, dz square. So if you have a tetrahedral splitting, they will split in different ways. dxy, yz, zx will be in higher energy, then dx square, y square, dz square will be lower energy. But if you have octahedral splitting, it will be opposite like that. So that was crystal field theory. So here you can see salient features. Central metal atom or ion is surrounded by various ligands which are either negative charge or neutral molecules. Electrostatic interaction between the metal and the ligand it is purely electrostatic. ಅಂದ್ರೆ 100% ionic ಆಗಿದೆ ಅಂತ ಹೇಳ್ತೀವಿ. For example, Fe minus and CO plus 3. Central metal atom, that is CO plus 3, it is having 5 degenerated d orbitals. ಯಾವ್ಯಾವು? dxy, dyz, dzx, dx square, y square, dz square. And these are the shapes of those d orbitals. When the ligands approach the metal ion, due to repulsion forces, the degeneracy of the d orbitals is destroyed and they split into two groups of different energies. Energies navenantivi T2G and EG orbitals. This effect is called crystal field splitting, which is denoted by delta 0 or 10 dq. So you can see here isolated atom or ion idaga all are having same energy. This is in increasing energy format. So they will split. They will split. So here octahedral idaga dx square y square dz square Eg anta barutte. dxy dyz dzx comes into T2G. Octahedral field crystal field ali. Due to the repulsion, the orbitals along the axis of the ligands acquire higher energy, while those lying in between the ligands acquire less energy. It doesn't show any overlapping. From the crystal field stability energy, the stability of the complexes can be known. So crystal field splitting antandrenu splitting of 5 degenerate d orbitals. Here we have crystal field stabilization energy. So change in the energy achieved by filling up electrons in the orbitals in the complex metal ion is called crystal field stabilization energy. Yenappa? Electrons in the T2G orbitals of an octahedral complex, if you see, are lower in energy while the electrons in each orbital. Just now we have seen here. You can see here. So T2G orbital olagirtakanta electrons, they are having lower energy while the electrons in EG, they are having higher energy. This is E. Yes or no? So illi nodbodu ನೀವು. So this is energy in the increasing form. So T2G are having lower energy octahedrally, whereas EG they are having higher energy. Howda? So here what is happening? The lower the total energy of the system, the more stable. Eshtu energy kadme irate, ashtu stability jasti irate. Crystal field stabilization energy, when we speak about CFSE of a complex, it is the measure of net energy. This is what we am talking about. Measure of the net energy of stabilization of a metal ions electrons. So this is 0 for weak field or high spin ligands. So I can write here crystal field stabilization energy is 0 for weak field or high spin octahedral D0, D5, D10 complexes. It is 0. Okay. So this is all about the crystal field stabilization energy. Okay. So here we were talking about factors which determine the splitting energy. Yes. Yavu factors determine agatte when we talk about the splitting energy. What are the factors? See, generally we say higher the ionic character ಅಥವಾ ionic charge on central metal atom, greater is the crystal field stabilization energy, denoted like this. Okay. The values of the complexes formed by metal ions belonging to 3D is less than 4D is less than 5D. So on going from 3D to 4D, we can say delta 0, that is delta O, that is the crystal field stabilization energy. It goes on increasing by how much? By nearly 50% it goes on increasing. So this is about the crystal field stabilization energy. Illi navu nodidvi. See, in this case, you have seen about the crystal field stabilization energy ಬಗ್ಗೆ nodidvi now. Here. So this was what example you have seen. This was in case of octahedral complex. But idanne nanu tetrahedral complex alli madbekappa antandre, I can show you that also. So if this is the energy form, okay, then I have, let me say, these are the degenerate d orbitals 3, 4, 5 isolated atomally. So dxy dyz E is in increasing form here. So what happens? So here metal ion in the tetrahedral complex, I am speaking about tetrahedral complex. Okay. In the tetrahedral complex, what happens? They will split. Yes, how do they split? They will split like this. 1, 2, 3, and here 1, 2. So here I have dxy, here I have dyz, here I have dzx. This is called T2G, and here dx square y square and dz square. This is called EG. This is called EG. Okay. So here you can see it is exactly opposite. How then Allah? Nodi nodana. This is exactly opposite of octahedral splitting. And this difference, the net difference here, what I'm saying, this is called delta naught. This is called delta naught. Yes. Delta naught anta ಹೇಳ್ತೀವಿ. Okay, fine. So, the crystal field theory is successful in explaining the formation of the structures, optical properties no chanag ಹೇಳಿತು, then magnetic properties also explained. However, it fails to explain the position of anionic ligands. ಇಲ್ಲೇನೂ drawbacks ಇದೆ. It fails to explain the position of the anionic ligands at the low end of the spectrochemical series. At the low end of the spectrochemical series, it failed to explain the positions of the anionic ligands. Anionic ligands, the position ಹೇಳಲಿಕ್ಕೆ it was not successful. Now the question arises, what is the spectrochemical series? Spectrochemical series anta andre ಏನು? So spectrochemical series is a very, again, it is also a very interesting point. So I'll write here spectrochemical series. So some series, something regarding ligands it is. So spectrochemical series anta andre, the ligands can be arranged. So I'll write here, ligands can be arranged in increasing order of their strength. What strength I'm talking about? It is ability to cause crystal field splitting. Okay, crystal field splitting. That is nothing but strength of ligands. And the series so obtained is spectrochemical series. Spectrochemical series. Okay, so this is spectrochemical series. So when I spectrochemical series ಹೇಗಿದೆಯಪ್ಪ ಅಂತಂದ್ರೆ, it starts from I can say it starts from weak field ligands and up to it goes to strong field ligands ಅಂತ ಅನ್ಬೋದು. So I'll write here, first I have I minus, then Br minus, then you have Cl minus, then F minus, OH minus, OX minus 2, then H2. I'm sorry. Let me take it in a proper form. So here I minus, Br minus, which is less than Cl minus. So first weak field ligands, then F minus, then OH minus, then OX minus 2, then H2O neutral ligand, then Py, then you have NH3, then En, then NO2 minus, then we have Cn minus, then we have CO. I'm sorry, we have CO here. Fine. So this is called spectrochemical series. So you can see here in the spectrochemical series, it starts from weak field ligands. How the weak field ligands to strong field ligands. Strong field ligands. So ability of the ligands to cause splitting. Field splitting, yes. So ligands arranged left to NH3. So you can see here, left to NH3 are generally they are called as weaker ligands, and they do not cause possibly the forcing of pairing of the electrons. Ivella cause madalla. Whereas ligands which are to the right side, 3D orbital pairing agalla, and they form outer inner orbital complexes. Inner orbital complexes. Howda? Inner orbital complexes ಆಗತ್ತೆ ಇಲ್ಲಿ. These all orbitals, weak field ligands. And if you see from at the right side of these, they will force the electrons from in the central metal atom to pair up. Yes, and they will pair up easily, and they will form outer orbital complexes. Outer orbital complexes. Because therefore they are called strong field ligands. Alva. So outer orbital complexes are formed very easily here. So this is about the spectrochemical series. You have certain organometallic compounds also. So organometallic compounds antandrenu, which they have metalloids there. Yes, preparations of applications anta nodidaga of yes, this applications become very important. Applications of coordination compounds andaga, estimation of hardness of water like Ca plus 2 ಮತ್ತು Mg plus 2 ions idu, they form complexes with EDTA. They form complexes with ethylene diamine tetraacetic acid. Therefore, that you can use it for as the estimation for of hardness of the water. The second one is animal and plant world. Very important. Now, nodidvi in the first session itself, chlorophyll agirbodu, which is a coordination compound of magnesium. Hemoglobin agirbodu, which is a coordination compound of iron. B12 vitamin agirbodu, which is a complex of cobalt, CO plus 2. Electroplating of metals involves use of complex salts like as electrolytes. For example, KAgCN2 is used in silver plating. It is used in silver plating. So this is also an application. Even I told in drug industries agirbodu, textile dyeing industries agirbodu, then many industrial catalyst preparations, reagent preparations ali we find applications of coordination compounds. Extraction of metals, silver and gold metals, they are extracted from the ores by dissolving in NaCN to form the complex only. Coordination complex agi form agate. Then estimation and detection of metal ions like Ni plus 2 ion is estimated using dimethyl glyoxime DMG. You can estimate the and also detect the metal ions there. Then medicinal options also. Cisplatin, it is used in very important. Yaudu cisplatin. It is nothing but cis PtCl2 NH3 twice. This is used in the treatment of cancer. Treatment of cancer. So these are the vast applications of what you can say, applications of our coordination compounds. Nam coordination compounds the applications anta anbodu. So this is all about coordination compounds. I hope the concepts are made very clear. Hope you enjoyed the sessions, all the 4 sessions. All the best for your competitive ways of solving the questions. For now, chalo, bye. Thank you. Take care.